welcome to this edition of Numerical Analysis, where we're going to be talking about polynomial interpolation. Specifically, we're going to talk about the Lagrange polynomial. Without wasting any time, let's get into it. So, the two most important formulas with the Lagrange polynomial are as follows. We have the Pn of x is equal to the summation from k to n of ln x multiplied by yn. Right? And then ln of x can be represented as the product of this formula here as from I to n, but I should not be equal to k. This is all just fancy mumbo jumbo, and let these operators not scare you or freak you out. This basically just means multiplication. That is, the Lagrange polynomial can be represented as, this ln can be represented as a formula. If you've been given three sets of data points, it can be represented as having L0, right? Because we have three data sets here, so meaning our n is equal to 3. So meaning our ln's highest polynomial is going to be L2, starting from L0. Okay, so if we have three data sets, which is 1, 2, 2, 4, and 3, 9, our polynomial for Lagrange is going to be equal to L0 of x, which is going to be this equation here, which is x minus xi, xk minus xi, and we're going to have this guy here, L1 with the same scenario, and L2 with that same scenario. So I want you to realize something here before we dive deeper into the actual schematics of this Lagrange polynomial. I want you to realize that we have this formula, which is x minus x1. This is a value that is 1 unit better than the other, than 0, sorry. So we have 1 and 2, units 1 and 2 for this guy here. Notice that because we have three data sets, we need to have L1 and L2. So meaning of what data set 1, data set 2, and data set 3 over there. So meaning x1, x2, right? And then we got x0. So our formula here is going to incorporate both x1 and both x2. If we had 4 data sets, we are going to incorporate x1, x2, and x3 on this other side here. But because we have 3 data sets, we're just going to incorporate 1 and 2 for x0, which is going to be the divisor in this scenario. x0 there and x0 there minus x1, x2. And the same goes for L1, where we only have data points that are not exactly L1. So we have x0 and x2, right? Divide by x1 minus x0, which is there, and x1 minus x2, which is also there. And then for L2, we have x minus x0 and x minus x1. And as we see that we have no x2 on the numerator here, and the divisor has x2 as the leading subtractor there, minus x0 and minus x1. So basically you have this type of relationship where you have these products, or sorry, these points multiplying with each other using this formula here and all that there. But this may sound like gibberish, so let me just give you an example basically. But before we get into that, let me just explain the tiers in the Lagrange polynomial. So the tiers of the Lagrange polynomial are as follows. We have linear interpolation, we have quadratic interpolation, and we have cubic interpolation, right? And all these can be represented as so. So linear interpolation, when you have, say, let's just say given two data points 0, 1 and 2, 5, interpolate the value of x1 using linear Lagrange polynomial. So basically when you're talking about linear interpolation, we are looking at basically 2 points. We have 2 points here, which is data set 0 and 1 there. So we have these steps that we can take. First things first that you want to do is you want to outline your data points. That is a very important key, and that is going to help you properly grasp the concept of linear or interpolation as a whole. So you have your data sets here. You've got the x coordinates and you've got your y coordinates for a data set 0 and data set 1. So meaning this is going to be x naught, and then this is going to be x1, this is going to be y naught, and this is going to be y1. Right? So for x naught here we have 0, y naught we have 1, and for x1 we have 2, and for y1 we have 5. So the second step is we need to find the point for L0 and for L1. So notice if we say linear interpolation, we're talking about, let's just think of it like saying x to the power 1, right? So think of these points here as powers. So when you say linear, you know that you're going to have two data points. If you say quadratic, it means that you're going to have L2 cubic, L3, and so on and so forth, right? So let's find L0. So for L0, because we only have two data points here, we're only going to have two data points. So we have 0 there, but because we can't incorporate 0 in the numerator here, we only have another data point that's there, which is x1. So we're going to just place x1 over there. And then on the bottom, we have x0 minus x1. Because this is linear, we're only going to just get this function and we're done. We're not multiplying it by any other value or anything like that. So we're going to say x minus 2, because the value of x1 is 2. So we're going to say 2x minus 2 divided by 0, because x0 is equal to 0 minus 2. And then we're going to just simplify this equation and say x minus 2 divided by negative 2 is equal to that value. But then, because we say that our x value is equal to 1, so if we substitute 1 where x is, we're going to have 1 minus 2, which is going to be negative 1. And negative 1 divided by negative 2 is essentially 1 divided by 2. Hope you see where this is coming from. Okay, so we also have L1. And for L1, because, again, we only have two data points, so we're only going to have this one expression here. And rather than having x1 here, or in this point, we're going to have x0 or x0. So x minus x0 divided by x1 minus x0, and which is going to equal to x minus 0 divided by 2 minus 0. And then if x is equal to 1, divide by 2, we're going to get 1 divided by 2, right? And we found L0 and L1, or L0 and L1. Great. So step 3, we're going to find the polynomial of P1, because we have this guy here. So we've got a linear polynomial. It's going to say P1 of x is equal to L0 of x multiplied by y0 plus L1 of x multiplied by y1. And once we have that relationship there, L0 here is 0.5 or 1 over 2 multiplied by 1 plus 0.5 multiplied by 5. Y0 is 1 here, so that's why we've plugged in 1. And 0.5 there is this value that's here, and then y1 is equal to 5. And then when you do your mathematics properly, you get the value of P1 of x, which is equal to 3. So we have interpolated this equation, or this linear equation, for lack of better terms. So we have found our value of P1 of x, which is equal to 3. So that's basically that with linear polynomials. And then we're going to go to quadratic interpolation next. So quadratic interpolation next. Basically, if you have 3 data points, and let's just say we have different steps, let's just say negative 1, 4, 0, 1, and 2, negative 1, and then we interpolate the value at x1 using the quadratic Lagrange polynomial. What we're going to do is we're going to go through the exact same steps and say you first outline your data points, and then once you've outlined your data points, you have these values outlined properly there. Second, we have to find L0, L1, and L2. So because it's a quadratic, we see that we have a 2 there. So quadratic, just know that the last value is going to be L2, right? Or X2, depending on what your preferences are. So finding L0, because we have three sets of data points here, so finding L0 here, we're going to have 2, X1 and X2. And then here we're going to have X0, X1, and X2. So on the bottom here, everything is incorporated, but on the top, X0 is omitted. So if we were to substitute the values of all this here, we're going to get to a point where we have -1/3 when you substitute for every x value at 1. And then we have L1, where this is L1, so meaning the value here is going to be x0 and x2, divided by x1 minus x0 and x1 minus x2. Notice that here we have L1 and we have x1 over there, and on the top here we only have x0 and x2. So it goes like that for as many times as possible with Lagrange polynomials. It's just the same format, constant. It's the same thing over and over again. So if you substitute and you do your mathematics correct, you'll get a point where you have 2 divided by -2, which is the same as -1, right? And then L2, so we know that L2 is not going to have x2 on the top. We're going to have x0 and x1, and we're going to have x2 at the bottom, subtracting x0 and then also subtracting x1. And if you do your mathematics correctly, you're going to get 2 divided by 6, right? So now finding the polynomial, we're going to say P2 of x is equal to L0 of x multiplied by y0 plus L1 of x multiplied by y1 plus L2 of x multiplied by y2. And when you substitute all those values that we placed here into this equation here, you do your mathematics and you get your value of -2.66 somewhere there, right? So it just keeps on going forward. So that's quadratic interpolation, nothing difficult here, same format. And if we were to go to cubic interpolation, we're going to get something of the same fashion. And we say given 4 data points, we have L0, L1, L2, and L3 to interpolate the value of x at 0.5 this time using cubic Lagrange polynomial. Solutions stay the same. We've got the steps, outline our data points, and we have our data points there. And we've got finding L0, L1, L2, and L3. And we plug in this formula, and then we see that for L0 we have x1, x2, and x3, but on the bottom we have x0 subtracting x1, x0 subtracting x2, and x0 subtracting x3. And then when you plug in the values and the formula there, you get a value of this guy, which is basically positive. Same thing with L1, where we notice that in here we have x0, we have x2 and x3, except from x1, but on the bottom we have x1 minus x0, and x1 minus x2, x1 minus x3, and so on and so forth. When you substitute your values, you're going to get 1.75 divided by 2, and same thing happens. Same thing with L2. Notice that we don't have x2 on the top, we only have x2 at the bottom. Substituting that value, you get this. And then L3, same scenario, where we have we don't have x3 at the top, but we have x3 at the bottom. And then substitute all that. Alright, so now once we found our data points there for L0, L1, L2, and L3, we're going to find the polynomial. And we substitute all the values that we have found into the polynomial expression, and then we're going to get our value of 4.125. And basically, that's it with Lagrange polynomials. So when it comes to this, you have 3 steps. So first things first, you collect your data points. Second, you find L0 and all the way up to Ln. And third, you find the polynomial. And yeah, this was a really short video. It's nothing really difficult with Lagrange polynomials. It's actually very easy to find these types of questions. And if you have any queries about anything, please comment down below, and I will